Hello, this is lecture 5 of computational methods, and in this lecture we are going to be talking about doing matrix operations numerically, or if you want me to be more technical about it, we are going to look at numerical linear algebra. For this, you can refer to the book by Newman, and the relevant chapters, the relevant sections over here are 6.1 and 6.2. Which by and large covers everything that we want to talk about, plus a few more things. But if you want to look at more details on these topics, as well as various other techniques which we will not have time to discuss, then numerical recipes is a good place to check those out. And in that, you can look at chapters 2 and 11. Yeah. So, why exactly do we care about doing matrix operations or linear algebra numerically? So, these topics have very wide applicability. Of course, all of quantum physics, quantum mechanics is based on linear algebra. So if you want to do any kind of numerical calculation within the framework of quantum mechanics, then of course you need to use the tools of linear algebra. Even apart from that, uh, any system which has a large number of different components that you want to work with. So for example, multiple equations with multiple unknowns. You can solve those with linear algebra. Any kind of network that you want to look at, whether it's an electrical circuit or some kind of an online network or a graph theoretical problem, again, linear algebra is very useful over there. Various probabilistic and stochastic processes also, you can apply linear algebra there. So it's a very common tool, one of the more commonly used tools of computational methods, numerical methods, with applicability in various fields. So we're going to spend this lecture studying these topics. So one of the most basic things that one might use matrix methods for is to simply solve equations simultaneously. So if you have two equations and two unknowns, or three equations and three unknowns, and so on, that's when you can use uh, these matrix operations. So the first topic we are going to look at is solutions of systems of equations, linear algebraic equations. And we are going to do this by a method called Gaussian elimination. So let's take one example. I have one example written over here. Suppose I want to solve simultaneously three equations and three unknowns. And the three equations that I'm interested in are 3x plus 7y minus z equal to 0, 2x minus 2y plus z equals 10, and x minus y minus 4z equals minus 4. So what I can do is I can write down these three equations. I can write them in a combined form as one matrix equation. So I can write this as, and you can see that this works out, 3, 7, minus 1. So I'm just taking the coefficients of x, y, z in each equation. Then second equation is 2x minus 2y, 1z. Third term is 1 times x minus 1 times y minus 4 times z multiplied by x, y, z. This gives 0, 10, and minus 4. So you can see if you just multiply these two matrices on the left hand side, or as we call it, this is a matrix A and this is a vector, let's call it X. On the right hand side you get a vector V. So you can multiply A and X and you can see that you will get exactly these three equations over here. So 3x plus 7y minus z equals 0 and so on. So we have gone from having to solve 3 equations to solving one matrix equation. So we want to find x where ax equals v. Find x. So that is the problem we are interested in. So in order to solve this problem, there are three kind of transformations that are allowed. So we are going to use a method called elementary row transformations. So basically this Gaussian elimination depends on what are called elementary row transformations. And these row transformations are the following. There are 3 of them. First is you are allowed to interchange any 2 rows. The second one is that you can scale a row by some constant. Means you multiply the entire row by some number. And the third is that you can add one row to another. And in fact, you can combine the second and the third rules to make one combined rule, which is that you can take, let's say, row 1 and you add to it k times row 2. That is allowed. So these are the elementary row transformations. And with the help of these elementary row transformations, we can solve this matrix equation that we have. So let's first solve it out by hand analytically. That will give you a feeling of what exactly these row transformations are, what they do, and how they help us in solving these equations simultaneously. So how much time do we have? Okay. So let's write down this equation again that I had. 3, 7 minus 1, 2 minus 2, 1, 1 minus 1 minus 4, x, y, z equals 0, 10 minus 4. Okay, so I'm going to now try and solve these equations using these elementary row transformations that we've written down. So the way to do it, first step, always make your 1 element equal to 1. So there are 2 ways of doing it. You can either divide the first, you can multiply the first row by 1/3, because rule 2 says that you can scale any row by a constant. So you can either multiply the entire first row by a factor of 1/3, or you will notice that this 1 element over here is 1. So you can also just interchange these two, because you're allowed to interchange rows. So that way you'll get a 1 over here in the 1 position. So let's do that. So first we interchange 1, and so let's call it row 1 to row 3. We interchange, and whatever you do on the left hand side, you also have to do it on the right hand side. So your equation becomes 1 minus 1 minus 4. Second row remains the same, nobody's touching it. Third row becomes what was the first row. So I've interchanged these 2 rows. I realized I called this one also x, which is the same as the small one x. So let's call this capital X. Is equal to, right hand side also have to interchange the first and the third row. So I get minus 4, 10 and 0. So okay, this term over here has become 1. Now I want to eliminate the 2, 1 and the 3, 1. I want to eliminate this, I have to make it 0, and I want to make this also 0. So the way to do it is I can say, so remember, I can always do row 1 plus k times row 2. So I will say, let my row 2 become row 2 minus 2 times row 1. So my row 1 is not being changed. Row 2 I'm replacing with R2 minus 2 times R1. So 2 minus 2 times 1 is 0. Minus 2 minus 2 times minus 1, that is also 0. This becomes 0, okay. And 1 minus 2 times minus 4 is 1 plus 8 is 9. And the same thing I must do on the right hand side. So first row remains unchanged. 10 minus 2 times minus 4. So 10 plus 8 is 18. So second row is done. Third row also I want to eliminate this 3 over here. So I will say R3 goes to R3 minus 3 times R1. So that eliminates this, that makes it 0. 7 minus 3 times minus 1 is 10. Minus 1 plus 12 is 11. This is not looking very nice. We'll figure it out. And over here, 0 plus 3 times 4, so that's 12. Okay. I thought I had taken nice clean equations. Why so messy? And we'll figure it out. Okay, the next step. So, see, in some sense, our first column has become very clean now. It has become 1, 0, 0. Now we want to also make, we want to do something similar on the in the second column also. So first thing I want to do is I want to make this element equal to 1. 2 element has to become equal to 1. So the way to do it is, well, this is 0. I can't multiply 0 by any number to make it 1. So scaling is not going to work. What if I interchange these two rows again now? So then this 10 will go over there. Yeah, I think that's a good idea. Let's do that. So now I say R2 interchange R3. So I get 1 minus 1 minus 4 because nobody's changing the first row. 0, 10, 11, and 0, 0, 9. X, Y, Z. Again over here, now I'm exchanging the second and third. Okay. Now how should I get a 1 over here? I can just divide it by 10. So I will say R2 goes to R2 divided by 10. So then I get, no, never mind, 1 minus 1 minus 4, 0, 1, 11 tenths, 0, 0, 9. Minus 4, 18 and 12 tenths. So I got a 1 over here, I'm happy. Now this element I want to make it 0, that is the next step. So because I want this column also to become 1 on the diagonal and 0 everywhere under it. But this is already 0, so very good, nothing to be done. Next step is to make this element equal to 1. Basically what we are trying to do is we are trying to make an upper triangular matrix. If you remember, an upper triangular matrix is one for which everything below the diagonal is 0. So that is what we are trying to achieve. And we are trying to make all the diagonal elements equal to 1. So how should I make this 9 1? Well, I can divide this entire row by 9. So R3 goes to R3 divided by 9. So nothing is changing in the first two rows. And this third row gets divided by 9. Now this is straightforward. Now if I do this matrix multiplication of this matrix and this matrix, what you will find in the third row, you will find that this is just, so 0 times x plus 0 times y plus 1 times z is equal to 2. So we've already found out what the value of z is. Now if you look at the second row, then you get 0 times x, 1 times y plus 11 by 10 times z equals 12 by 10. But now you already know that z is equal to 2, so I can substitute that. And from this you get y equals 12 minus 22 is minus 10. So it is minus 10 by 10, which is minus 1. And if you look at the first equation, the first row of this matrix equation, then that is x minus y minus 4z equals minus 4. But you already know what y and z are. So the x plus 1 minus 8 equals minus 4. So what is x? 4 minus 1, 3 I think, no? Is it? X minus... See, this is the problem with being a theoretical physicist. I can calculate the curvature around a Schwarzschild black hole like this, but minus 4 plus 8 is plus 4, and plus 4 minus 1 is plus 3. Yes, I think x is 3. Very good. So this is my solution. X is 3, y is minus 1, z is 2. So what we did was, there were basically two steps. First step was to convert the matrix A into an upper triangular matrix, meaning all the elements below the diagonal have to be 0. Once you have done that, then it's easy to just write down the equation, and then it's a question of just back calculating what x, y, z are, because directly you get what z is. And then from that you can go back and find out what y is. From that you can go back and calculate what x is. Actually, you don't even need to do this. You can also continue doing these elementary row transformations. This is of course one way of doing it. The other is, suppose we were over here, no? Let's write this again. 1 minus 1, 4. So I'm taking this equation over here. 0, 1, 11 tenths, 0, 0, 1, x, y, z, minus 4, 12 tenths, 2. Very good. I can just continue doing some more elementary row transformations. Since this element is already 1, I can try to eliminate this one, make it 0. And to do this, what will I do? I will say let R1 become R1 plus R2. So 1 plus 1 will become 2. So will become minus 1 plus 1 will become 0. So the second row remains unchanged in this. Third one also remains unchanged. It is only the first one which is changing. So 1 plus 0 is 1. See, nothing will happen to this one. It will not be affected because there is a 0 sitting over here. We've already taken care of that. Over here, when I add, I get 0. And what is minus 4 plus 11 tenth? Minus 4 plus 11 tenth is minus 40. So this is minus 29. Okay. and over here I have minus 4 plus 12 tenths, so minus 40 minus 28. And now same thing we can do in the third column. Now I want to eliminate this one and this one. So what I'm doing here is nothing happens to R3, but R2 goes to R2 minus 11 tenth of R3, and R1 goes to R1 plus 29 tenth of R3. That will take care of those two. So in the end, I will get two. What is 12 tenths minus 11 tenths? 12 tenth minus 11 tenth times 2. So this is minus 1. And similarly over here, minus 28 tenth plus 29 tenth times 2. So this is 58, 33. Is this what we had? 3 minus 1, 2. 3 minus 1, 2. Correct. So this is the final answer. What we have done is we have converted our matrix A that we had by doing these row transformations. This matrix we have converted into the identity matrix. So basically we now have I times X equals 3 minus 1, 2, but identity times any matrix by definition is just X. So this is the solution. So by doing these elementary row transformations, we have reduced our matrix A. So we started with AX equal to V, and then we did some elementary row transformations, and either you make this an upper triangular matrix in which, and similarly this becomes some V prime. So let's call it some A upper times X equal to some V prime, let's say. And then by back substitution, you can calculate what the elements of X are going to be. Or the other way is, you started with AX equals V. Then by doing elementary row transformations, you convert this A into the identity matrix. So you get I times X equals, and meanwhile this gets converted into some V double prime, let's call it. So then X is just equal to V double prime. So calculating by hand numerically, this is how you would go about and solve these kind of linear equations simultaneously. So what can we do now numerically? Let's go back. Let's try and generalize these steps a little bit. I'll write it in a different color. I'll write it in blue. So what we did over here in this step was, we said let R2 go to R2 minus, what is 2 now? 2 is basically A21 times R1. It's the 2, 1 element of this matrix. And similarly, R3 goes to R3 minus A31 times R. Oh, actually we should start over here. No? When we are saying R1 interchange with R3, what we are saying is A1. So if I refer to the elements of the matrix as A, I, J. So I represents the row number, J represents the column number. So when I'm interchanging two rows, what I'm saying is, first row, any of the column elements has to be interchanged with A3J. That is what I was saying over here. And I said interchange rows 1 and 3. So for all j, so think of it as a, when you're doing programming, think of it as a loop over j. So j going from 1 to 3, j going in range 0 to 3. You're saying a1j and a3j get interchanged. Then similarly over here, this is basically saying a2j equals interchange with a3j. Then what we did was r2 gets replaced by r2 divided by, this is a22. Notice that at each step we are changing our definition of a. So at every step we are updating what a is. So initially we had some original a, but then once you do this interchange, then you get a new matrix. Now this is what I'm calling a. So then in this, when you're doing these steps, your a has changed. Then after having done these elementary transformations, now this is your new a, and so on. So at each step I'm updating what I mean by the matrix a. It's not the original a that we started with. Similarly over here, R3 goes to R3 divided by, what is this now? This is A33, and so on. So the way that we are doing, and similarly over here also, I'm not writing out explicitly at each step what it should be, but the idea is as follows. First, always check, first make A11 equal to 1, either by scaling the row or by interchanging. Second, actually, okay, if you want to write a general program, don't do interchanging. It's better always to do scaling. First of all, check if A11 equal to 0. If A11 is not 0, then just divide row 1 by A11. So R1 goes to R1 by A11. But if A11 is equal to 0, then you can't scale the entire row by A11. So what are you going to do? Then you interchange A11, you interchange your entire first row with whichever row under it doesn't have a 0 sitting in that first column. So if A11 is 0, then interchange R1 by any row j whose first element, so aj1 is not 0. So having done this interchange, now and then do R1 going to R1 divided by A11, because now A11 is no longer 0, so you are allowed to divide by it. So having done this, your matrix has got a 1 over here. So these are all some numbers, but you managed to get a 1 over here. Next step is to make these two 0. So the second step is R2 goes to R2 minus A21 times R1, because right now this is A21, this is A31. So you want to divide this row, the second row, by A21 times, you want to subtract it, you want to subtract from it A21 times the first one, so that this becomes 0. And this you want to subtract by A31 times the first row, so that this becomes 0. Excellent. Next step is to check is to make this one equal to 0. So third, check if A22 equal to 0. If not, then R2 you divide by A to 2. Basically exact same thing as you did over here, except for the second row, second column. So 2, 2. But if it is equal to 0, then again you interchange now row 2, interchange row 2 with any row below that, so that now you're such that AJ2 is non-zero. And now having interchanged that, now you can do R2 going to R2 divided by A2. So now our matrix has become 1, 0, 0. Here there are some numbers, and this one you have managed to make 1. Now you want to make this fellow 0 at the bottom. So then R3 goes to R3 minus. So right now this is some A 3 2. So minus A 3 2 times R2. So that will turn this one into a 0. And you keep going on like that. Similarly, you do the third one. Of course, this is for a 3 cross 3. In general, you have a bigger n cross n matrix. You keep doing this step. You keep doing this procedure n times, one for each row. And that way you will have ensured that you have reached either an upper triangular matrix or a diagonal identity matrix, as the case may be, depending on whether you want to use this method or you want to use this method.